Now that we've talked about marginal product, we can move on to thinking about production functions with more than one input. We're going to typically have production functions with two inputs, and this is so that we can show the difference in trade-offs in production between fixed and variable inputs. Fixed inputs are fixed. They cannot change in the short run, while variable inputs can change in the short run. So to describe production with fixed and variable inputs in one function, we want to characterize an isoquant. An isoquant is an equation that describes all the possible combinations of inputs that can be used to produce a given level of output. This is kind of analogous to our indifference curve in our utility function, where we tried to think of all the combinations of goods that yielded a given quantity of utility. But here we're thinking about combinations of input to produce output. So let's take a production function like we have here, L to the 1/2, K to the 1/2, and plot the isoquant for Q is 20. So we want to produce 20 units of output. We can do that using lots of different combinations of labor and capital. So to find the equation, we're just going to plug 20 into our production function. And again, the math here is exactly the same as when you're plotting your indifference curves. We'll square both sides so that we get rid of those pesky 1/2s. And we get K is equal to 400 over L. So really we're trying to find two variables that multiply together to equal 400. So I've got 10 and 40, 20 and 20, or 40 and 10. 10, 40, 20, 20, 40, 10. And here is my isoquant for a level of production of 20 units of output. Just like when we talked about indifference curves using our utility function, when we're thinking about our isoquants, we want to think about the slope of the isoquant, and its name is the marginal technical rate of substitution. The marginal technical rate of substitution tells me how much capital I would need to replace 1 unit of labor, maintaining a constant level of production. And we find the marginal technical rate of substitution by taking the ratio of the marginal product of labor to the marginal product of capital. So this is the rate at which we need to substitute capital for labor in order to hold production constant. In this example, we can calculate the marginal technical rate of substitution. And we want to do that at the quantity labor is 10, capital is 40. So we need to find marginal product of labor, which will be 1/2 L to the negative 1/2 K to the 1/2. Marginal product of capital, 1/2 L to the 1/2 K to the negative 1/2. And then when we divide, we get L on the bottom and K on the top. If we plug in our values for capital and labor, you can see that in this situation, we would need 4 units of capital to make up for the loss of 1 unit of labor. Remember that because what we're plotting here is the slope of the isoquant, that this ratio is really only valid for small changes around this point. Labor equals 10 and capital equals 40. Also notice that the marginal technical rate of substitution will diminish as we add more labor to our production function. In other words, as we add more labor, labor becomes less and less productive relative to capital. And that's due to the diminishing marginal product that we talked about in the previous videos. So for our production function, we will assume we have diminishing marginal product, and that results in a diminishing marginal technical rate of substitution, giving us these, again, nice convex isoquants. We will look at a few other types of production functions, this one that have different assumptions, but it's important to understand why this production function has this shape.